All right, so this is basically, well, more or less, problem 18a and 2.7, which I didn't assign, but I kind of thought would be worth talking about since we're kind of chilling here. This gets to something that we're going to talk about a little bit later, which is kind of dimensionality of stuff that's not vector spaces, or maybe that's not obviously a vector space. So let's think about how many entries do we need to determine a 5 by 5 symmetric matrix. So how many entries are there in a 5 by 5 matrix?
My dumbest guess is 25.
Your dumbest guess is correct. So this has kind of generally has 25 entries. Right? So those are A11, A21, A31, A51, dots in there, obviously. I don't know, I dotted one friggin' entry. And then this one's A12, and over here we have A15, and down here we have A55, right? Okay, so if this matrix is symmetric, what does that mean?
It means we can transpose it and it'll still be the same.
Yep, it means it'll be its own transpose, right? So if I think about what transposing means, that means that I would switch this entry and this entry, right? What other entries would I have to be switching here?
All of them
A31 and
except the diagonal.
Yeah, everything except the diagonal needs to get switched, right? I don't know what I did there. Sorry, that was probably really disconcerting on your end. Yeah, so I'm gonna have to switch everything across the diagonal, right? So everything that's gonna be below the diagonal here is gonna have to be the same as what it is above the diagonal up here. You guys with me on that? Okay, so how many entries are there below the diagonal here?
Ten.
Okay, how'd you get 10? There's one in this row.
Subtracted 5.
Oh, that's good. Yeah.
what I did was I subtracted 5 from the diagonal and then left with 20 divided by 2.
Good. Perfect. Yep. So the diagonal accounts for 5 entries, and then half of what's left is above and half of what's left is below. Perfect. Yep. So I know the diagonal is 5 entries, and the lower triangle is 10, and the upper triangle is 10. And so how many entries does it take to determine a 5 by 5 symmetric matrix? What's the ultimate answer to this?
Your Honor, can you repeat the question?
So what's the ultimate answer here? How many entries are free? Like how many numbers can I pick in a 5 by 5 symmetric matrix?
Would it not be 25?
It is not 25. For this reason. If I'm allowed to pick them all, I can do this. Right? Is this matrix symmetric? Why not?
So you can only Sorry, I cut you off. My bad. Keep going.
No.
I think you can only pick the diagonal. You can only pick 5 of them.
No, I was thinking you could only pick the diagonal plus 1/2. You know, so you can pick 15.
Yep. Very nice. So you can pick either the diagonal and the lower half, or the diagonal and the upper half, or you can do this weird mix match thing where you pick some of the upper half and some of the lower half, right? But ultimately, yeah, I'm going to think about it like this. These are free, and the rest are determined. So there are 15 independent entries in a 5x5 symmetric matrix. You guys with me on that?
Question: what would happen if we had 6 or a 6x6? How many free entries?
Good. So
I think
in
it
the
would
six-
be easier to do a 4x4.
Okay. So in the 4x4 case, right? How many entries are on the diagonal?
4.
Okay. And then how many are left?
12.
And so the lower triangle contains?
6, and the upper contains 6. So then that means we would have free of 10.
Yep.
Is there any way to I don't know, maybe this isn't, the number of free isn't as important as what you're trying to get at, but is there a way to guess the number of free variables or intuitively know it?
Yeah, I mean, I think we could come up with a formula, right? So what have we been doing? So if we're thinking about n by n symmetric matrices, right? How many entries are on the diagonal of an n by n matrix?
And
N. And then how many are left? Sorry, leftover is a crappy word. How about the lower triangle and the upper triangle? How many entries are in those two together?
n times n minus n.
Good. N squared minus n. And so all told, in just the lower triangle, there are
N squared minus n over 2.
n squared minus n over 2. And so the total number of free things is n plus n squared minus n over 2 free variables. This is a little weird. It feels a little screwy that n squared minus n over 2 thing always yields an integer, doesn't it? So I'd need to convince myself that n squared minus n is always even, yeah? Is that true?
Well, for it to be symmetric, it's got to be a square matrix, right?
Yeah, that's true.
So, that means that n times n is always multiplied by itself. So if it's an odd number, it gives an odd number, and then subtract an odd number from an odd number, and you get an even number.
Okay. And in the case that it's even?
It doesn't matter.
It doesn't matter because an even number times an even number is even, minus an even number is an even number.
And divided by 2 is still an even number.
Well, it's going to be an integer at least. It won't necessarily be an integer. Or sorry, it won't necessarily be an even integer, but it will be an integer. And integer is what's going to matter here. There's another way to see this, which is kind of fun. N squared minus n factors into n times n minus 1. And so either n or n minus 1 is even. Right, because these are two consecutive numbers. One of them is going to be even. And the product of an even number and an odd number. In fact, here, right, we know that n times n minus 1 is always going to be an even number times an odd number, right, which is always going to result in an even number. This has been your little number theory lecture for the day, randomly interspersed in here. The interesting thing here, the reason that I wanted to talk about this at some point in this course, is that you can think about the symmetric matrices as a vector space. And then these number of free variables are telling you the dimension of that vector space.
I don't immediately see that.
That's okay. We're going to talk about it more later, and it's going to really twist your head off later. I just don't want you to be surprised when I start talking about the dimension of a matrix space. It's just the number of free variables. That's all it's going to mean. You guys kind of good with this? At least with the counting part, that's okay. You don't, the matrix space thing, that can leave your head for a minute. All right. Let me stop that.